I want to talk today about infrared spectroscopy. It's a type of spectroscopy where we look at the vibrations and stretching and bending in molecules. I don't want to talk about the theoretical aspects of it today, though. I want to focus on how we use it, particularly how we use it in organic chemistry. In organic chemistry, it's primarily used to identify the presence of functional groups. What we do is we look for peaks characteristic of specific functional groups. And I want to look at some examples of that and show you what I'm referring to. And we're going to start with some of the most common ones and look at some that are a little less common. I want to start first with the IR spectra of 2-butanol, which is an alcohol. And alcohols have very characteristic OH stretches. This big, long, broad, curving peak above 3000 tells you this molecule has an alcohol in it. Next, I want to look at the IR spectrum of 2-pentanone. And anything with a C double bond O is going to have a very characteristic peak around 1700. You can see it's usually the deepest peak in the spectrum. It goes all the way down to the bottom essentially, and it's going to be just around 1700. This is a ketone. You also will see that with aldehydes. This is the IR spectrum for pentanal. It's an aldehyde. You can see the C double bond O peak at about 1700, just above. What I want you to notice is aldehydes also have a peak for this hydrogen that's down around 2700. So they're the only thing that you're going to see that in is down around there. Now when we have our carboxylic acid, we have both a C double bond O and an OH, so we might expect to see the C double bond O peak and something related to the OH peak. You can notice that they're, and we do see that, you can notice that they're both a little bit broader than in the case of ketones and alcohols. That's because there's a lot of hydrogen bonding involved, but the general trends are there, C double bond O and OH. This molecule also has an ether in it, which gives us some peaks down here, but we're not going to worry about those right now. If we look at a simple alkane with no other functional groups in it, like this 3-methyl hexane, what you're going to see primarily is this peak right here. This peak right here are from CHs. In particular, this peak right here, just below 3000, is from a hydrogen on a carbon that has all single bonds. So it's sp3 hybridized, not sp2 hybridized. There's no double bond here. It's a single bond. If we look at the IR for 2-hexene, an alkene with a double bond, we see a couple of new peaks. First, we still have the peak from the C single bond CH because we have a lot of CHs on, we'll have a lot of hydrogens on sp3 hybridized carbons still. This is the same peak we saw in our alkanes, but we've got this new peak just above 3000. This is just below 3000. This is just above 3000. For the C double bond CH, a hydrogen on an sp2 hybridized carbon. So there's sort of a dividing line right here at 3000. Below 3000 are the hydrogens on the sp3 carbons. Above 3000, the hydrogens on the sp2 carbons. We also want to look at this peak right here. It's at about 1650 or so, a little bit lower than the C double bond O peak. This is from the C double bond C. It's a little bit lower in frequency. Compared to the C double bond O peak, as I said, 1650 versus 1700, it's also a little bit weaker. So these are the peaks we look for in our alkenes. Okay, so when we look at aromatic compounds like this ethylbenzene, we might expect to see some of the same things we see in alkenes, which we do. We have the peak from the C double bond C. We have the peak from the CHs on the double bond, the sp2 carbons. We have the peaks from the CHs on the sp3 hybridized carbons, but we also a lot of times on aromatic compounds see these little peaks right here in this region. And whenever you see something in that region, that should tell you that your alkene is probably aromatic. Again, for an ester, C double bond O, C single bond O, around 1200, around 1700. In a primary amine like this para-ethyl-aniline, you should see peaks from the hydrogens on the nitrogen. A lot of times, not always, but a lot of times, when it's a primary amine with 2 hydrogens there, you'll see 2 peaks. Primary amine like this one, a lot of times you expect to see one peak here. And since these peaks are coming from the hydrogens on the nitrogen, if it were a tertiary amine, so a secondary amine with one hydrogen would have one peak, primary amine would have two peaks, a tertiary amine with no hydrogens there, we would not expect to see a peak here at all. Functional group I want to talk about, and I had to pull it up from this website because I didn't have any examples of it on my computer, are alkynes. And for an alkyne, you'd expect to see a bond, a peak here for the C triple bond C, and you expect to see a peak here if it's a primary alkyne. So this is a primary alkyne. It has a CH bond, which shows up here. And it has this bond right here, C triple bond C, which shows up right there.